Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
Last week, we got a high-level overview of the main concepts of statistics. Today, we'll continue to explore statistics by learning how to create some fundamental statistical visualizations using several different Julia plotting packages. By the end of this tutorial, you'll be able to create a linear regression, a histogram, and a density plot. I'll show you 3 different ways to do that. First, I'll teach you how to generate these plots manually using the plots package with the GR backend. Next, I'll show you how to automatically generate these plots using the StatsPlots package with the PlotlyJS backend. Finally, I'll show you how to generate presentation quality statistical plots using CairoMakie. This should be a fun tutorial, so let's get started. Open VS Code and maximize the terminal panel. Start the REPL by hitting Alt-J, then Alt-O. Make a new directory called tutorial02x05 by using the make directory function. Change your present working directory to your new directory by using the change directory function. Enter the package REPL by hitting the close bracket. Activate your new directory by typing in activate space period, then hit enter. Add the following packages and versions. I know that's a lot of packages, but these packages will allow us to do some really cool stuff, so just hang in there for a little while as they load. Type in status to confirm that all of the correct packages and versions have been added. Exit the package REPL by hitting backspace. Minimize the REPL. Create a new file by going to File, New File. Save the file as tutorial02x05.jl by going to File, Save As. Be sure to save your file in your new directory. I don't think I mentioned this last time, but it looks like VS Code has updated, so you don't have to scroll all the way down to the bottom anymore to get to the .jl file extension. It's listed in alphabetical order now, where you'd expect it to be.
Nice.
Go to View, Command Palette, and select Julia Show Plot to reveal your plots panel. I'm placing my plots panel behind my editor, but you can dock it anywhere that works for you. I'm going to be adding a header to my file, but there's no need for you to type this in. You can access the source code for this tutorial in my GitHub repository. The link is in the description below. Let's start by adding some data. We're going to use the calories data from the last tutorial. However, we're going to rename it Observations. Let's imagine that this data represents your observations while running an experiment in the lab. Every hour, you collect a sample, take a measurement, and then record your data. You do this for 20 hours. I've included a copy of the observations vector in the description below, so you can just copy and paste it here. Select the data and hit Shift-Enter. Let's also set up a vector containing the integers 1 to 20, which will represent the hour when you recorded your observation. Okay, now we're ready to start generating some plots. Let's plot our data to see what the default plot looks like. We're going to be using the GR backend, which is the default backend to the plots package. According to their website, GR is a universal framework for cross-platform visualization applications. GR was developed by the Scientific IT Systems Group at the Peter Grunberg Institute at, I'm not even going to attempt to pronounce this, which is one of the largest research centers in Germany. The main development of GR was done by Joseph Heinen, who currently maintains the software. gr.jl is the Julia interface to GR. It's the default backend to the plots package, so there's no need to add it separately if you're going to use it as a backend. However, you can use GR as a separate plotting package without plots. In this tutorial, I will not be covering the use of GR as a separate plotting package. When setting up your plot, you can use any size resolution you like. This is my setting, but feel free to set your own depending on your preferences. Let's create our first plot. Click on the Plots panel. You should see a line plot showing your observations over time. As an aside, try moving the borders. You should see your plot automatically resize. This is another recent fix in VS Code because it wasn't working when I started this tutorial series a few weeks ago.
Nice.
The line plot is the default plot for many plotting packages. However, when it comes to statistical plotting, you should try to avoid using line plots. A line plot implies that your data points are somehow connected and that you have knowledge of what's happening in between your observations. In this case, your data points may or may not be connected, and we do not have any knowledge of what's happening in between our observations. In order to more accurately reflect our knowledge of our dataset, rather than using a line plot, use a scatter plot instead. If you click on the Plots panel, you should see your same data, except now it's represented by individual data points, which is what we're looking for. Now let's calculate the mean and standard deviation for our data, so we can add that information to our plot. In order to add something to an existing plot, you can add the bang syntax to your plotting functions. The hline function will add horizontal lines to your plot. It requires the y-coordinates to be entered in as a vector. Now, your plot has horizontal lines showing the mean as well as the standard deviation on both sides of the mean. The mean and the standard deviation only show information about the observations. It does not show any relationship between the observations and any other dataset. In order to better understand the relationship between the observations and some other set of data, we can use a linear regression line. The linear regression line is some arbitrary line that is placed between the data points. The slope and placement of that line is determined by measuring the distance between the data points and that line along the y-axis, or the vertical distance. Those differences are then squared to eliminate the negative numbers, and then the squares are added up. The result will be either an upward sloping line or a downward sloping line, depending on your data. We can use the GLM package to find this line for us. GLM stands for Generalized Linear Models. I'm not sure who the primary author is of this package. We will be using the ordinary least squares method included in the GLM package in order to estimate our unknown parameters. The model that we will be using requires the input data to be in the form of a table. A table is a unique Julia data type. A Julia table is basically a matrix with identifiers for column headers and rows. There are several ways in Julia to create a table, but many of them require adding a large package, like data frames. Sometimes you just want a small package to convert your data into a table. That's what the type tables package is for. Again, I'm not sure who the primary author is, but it's a useful little package. To create a Julia table, use the table function from the type tables package. Here, the uppercase X and Y are the column headers. You can see that data is of type table. The X column contains the numbers 1 to 20, and the Y column contains the observations. Now, we can run this data through the GLM linear model to find a fit. There's a lot of information that's displayed, but the two numbers that we're looking for are in the coefficients column. In math, the formula for any line is described by y equals ax plus b, where a is the rise over run slope and b is the y-intercept. In this table, the intercept number of 163.7 is the y-intercept, and the negative 2.99 is the slope. So, the formula for our linear regression line is y equals negative 2.99 times x plus 163.7. The GLM package also includes a function called predict that will predict the y value of the regression line given any x value. We can use this function to plot our linear regression line. You should now see a downward sloping red line on your plot. That's the linear regression line that estimates the relationship between time and your observations. These type of statistical plots often show the formula for the line as well as an r-squared number. So, what's the r-squared number? R-squared is a statistical measure that shows how much of the variance in your data is explained by the relationship between the data on the x-axis and the data on the y-axis. It's a number between 0 and 1. The higher the number, the more your variance has been explained. The lower the number, the less of your variance has been explained. Rather than going through the manual calculation, I'm going to show you where to find it using GLM. In our example, an r-squared of 0.34 is not very good. It says that the time-observation relationship only accounts for 34% of the variation. So, something else explains the other 66%. Before we go, let's take a closer look at the predict function. Here, the predict function generated a 20-element array containing the y values of the linear regression line, which corresponds to the x values in the array T. What if we wanted to estimate the y values for some x values where we do not have any observations? First, we would have to set up a new table containing the new x values that we are interested in. Then, we can use the predict function again, but this time including new x as an argument. Doing this will generate an array which estimates the y values based on this OLS model. What happens if we enter in x values that go beyond our observations? Your model will give you, quote-unquote, predictions for x values outside of your observations, since it's just an imaginary line that goes from negative infinity to positive infinity. The temptation will be to use the y value output to either interpret the past or to predict the future. You should resist that temptation. The linear regression line is merely a best fit line for the known observations. It's not an archive for past events, nor is it a forecast model for future events. It's possible that the actual curve slopes up and down, and that your observations just happen to be at a point where the curve is sloping down. Based on your observations, you cannot make a global inference that all data is downward sloping in the past, or that all data will be downward sloping in the future. Save this plot before moving on to the next plot. Our next statistical plot is a histogram. I'm sure you've seen these before. A histogram takes your data and places the data points into bins, which is some range of values. The height of each bin represents the frequency of data points that fall within the range of that bin. It provides a quick visualization of the distribution of your data. In order to create a histogram manually, you need a model that will fit your data into a histogram. You can then take that information and plot it using a standard bar plot. You can find the model to fit your data in the stats base package. Before running your model, you need to decide on how many bins you need. A good rule of thumb to generate your initial pass is called Sturge's rule. Next, we need to fit our data into a histogram. This creates the bins, and then takes your data and places the data points into the appropriate bin. In this model, the bins are called edges, and the frequency counts are called weights. You can access this information by using the dot syntax following the variable name. Notice that it created 12 bins and not the 11 that we asked for. This is done to create standard size bins. Now it's time to generate our histogram. Your plots panel should now display your manually generated histogram. Not bad, right? Now, you can use any plotting package you like, even if it doesn't have a built-in histogram option. Let's add the mean and standard deviation information to this plot. The v-line function is the same as the h-line function, except it generates vertical lines instead of horizontal lines. Looking at the histogram, it's easy to see that our data is skewed to the right, with a high concentration of data within a relatively short range to the right of the mean. The data to the left of the mean is more spread out. Go ahead and save this plot as well. Our next statistical plot is the density plot. You may or may not have seen these before. While the histogram has been around for a long time, the density plot is relatively new. The density plot is similar to the histogram in that it displays the distribution of your data, but the density plot represents the distribution as a smooth curve as opposed to binned rectangles. In order to generate a density plot, you will need to create a kernel density estimate, or KDE, which you can do with a kernel density package. I'm not sure who the primary author is for this package. In order to create a kernel density estimate, all you need to do is pass your data into the KDE function. The output of the KDE function is a little difficult to understand. Let's generate the plot first, and then we'll revisit this output to see if we can get a better understanding of it. Let's add the mean and standard deviation information as well. Let's take a look at this plot. It definitely looks like a smooth curve version of our histogram. However, the units along the y-axis are unfamiliar. Rather than displaying counts, it shows something called density. The numbers are too small to be percentages, so what is density? It may be difficult to imagine, but the area under the curve adds up to 1. The way you calculate it is by multiplying each of the density figures by something called the bandwidth. You can access the density vector with d.density. This returns an array with 2048 elements, which are the y values on our plot. This is the equivalent of the counts in a histogram. Along the x-axis, rather than having 12 bins, there are 2048 so-called steps, or the bandwidth. You can see the bandwidth by using the step function. You can think of these numbers as the height and width of a very skinny rectangle. The area of each of these skinny rectangles represents a probability. The sum of all of these probabilities should add up to 1. Which it does. So, now that we know what a density plot is, what are some of the pros and cons of using it? On the plus side, the density plot shows the distribution of your data that is independent of the count, so it's easier to compare density plots with different sets of data. On the minus side, the density plot tends to show a distribution where no observations exist, which can be misleading. In any event, it's relatively easy to generate both a histogram and a density plot, so you can generate both and go from there. Before moving to the next section, save your plot. The next few sections will go much faster, since we're just going to be generating the same plots, but using different plotting packages. Before starting this next section, close out of the REPL by hitting Ctrl-D, and then restart the REPL by hitting Alt-J, then Alt-O. This will clear the memory and allow us to use another plotting package without any conflicts. Unfortunately, you'll have to repeat the startup process by changing the directory by using the Change Directory function. Enter the package REPL by hitting the close bracket. Activate your new directory by typing in activate space period and then hit enter. Exit the package REPL by hitting backspace. Go to your plots panel. On the top right, click on the 3 dots. Select Julia Delete All Plots. You'll also have to re-enter your data. Fortunately, you can just copy and paste it from above. Next, let's select the StatsPlots package and use PlotlyJS as the backend. Remember to enter in PlotlyJS all in lowercase. The primary author of the StatsPlots package is Tom Breloff, who is also the primary author of the plots package. StatsPlots is like plots, but on steroids. Like plots, StatsPlots is not a plotting package. It's a front end with a lot more functionality and plotting options than the plots package. Let's see how we can use StatsPlots to generate a linear regression on a scatter plot of our data. We can create a linear regression line by adding the keyword argument regression equals true. This code creates a scatter plot with a regression line built in. Nice, right? And with PlotlyJS, you have access to all of the interactive functionality. The keyword regression is not unique to StatsPlots. You can use it with plots and GR as well. I didn't mention it earlier because I thought it was important to understand how linear regression lines were created. Also, using the keyword regression here doesn't provide you with a formula for the regression line, nor does it provide you with the R-squared value for your data. For that, you still need to run the GLM model. One downside to using PlotlyJS is that the on-screen plot doesn't dynamically resize in VS Code. Try moving the borders around. This means that once you've set your dimensions, you're stuck with them for the rest of your session. Now, let's add the mean and standard deviation values to the plot. So that was easy, right? Go ahead and save your plot. Now let's generate a histogram using StatsPlots and PlotlyJS. We need to recalculate Sturge's rule, but you can just copy and paste it from above. We can generate a histogram using the histogram function. This histogram looks a little nicer than the one we generated manually using a bar plot. Although, it gave us 12 bins as well, instead of the 11 we asked for. You can use the histogram function using plots and GR as well. Again, I didn't show it to you earlier because I thought it was important to learn how to create histograms manually. Let's add the mean and standard deviation information to this plot. Looks good. Go ahead and save this plot. Now, let's generate a density plot using StatsPlots and PlotlyJS. You can generate a density plot by using the density function. Easy, right? Now, unlike regression and histogram, you will not be able to generate a density plot using the plots package. You will need to use StatsPlots for density plots. Let's add the mean and standard deviation information. Go ahead and save your plot. Finally, let's take a look at how to generate statistical plots using CairoMakie. Like before, you'll need to close out of the REPL by hitting Ctrl-D, then restart the REPL by hitting Alt-J, then Alt-O. This will clear out the memory and allow us to use another plotting package without any conflicts. You'll have to repeat the startup process again by changing the directory by using the Change Directory function. Enter the package REPL by hitting the close bracket. Activate your new directory by typing in activate space period and then hit enter. Exit the package REPL by hitting backspace. Go to your plots panel. On the top right, click on the three dots. Select Julia Delete All Plots. You'll have to re-enter your data. Fortunately, you can just copy and paste it from above. Next, select the CairoMakie package. Let's see how we can use CairoMakie to generate a linear regression on a scatter plot of our data. Before I move on, I wanted to address a question that I received in the comments section on a previous tutorial. The questioner was asking how to select different fonts using CairoMakie. Here's how to select different fonts. I'm using a Windows PC, and all of my available fonts can be found at this directory. With CairoMakie, you can use any font that's on your machine. CairoMakie has been updated since my last tutorial on CairoMakie, which was just a few weeks ago. They are now using the figure function to initialize a new scene and layout. Notice in the Plots panel that your layout is using a different font. Change Font 1 to Font 2 and then reinitialize the plot. I'm going to cycle through these fonts quickly so you can see that they all work. We'll use the Times New Roman font for the rest of our plots. Let's go ahead and generate a scatter plot. Try moving the borders. The size of the plot should adjust dynamically. Let's add the mean and standard deviation information. Unfortunately, there's no regression keyword argument available in CairoMakie. Of course, we can generate it manually like we did before. Not too bad, right? Go ahead and save your plot. Now, let's generate a histogram using CairoMakie. First, we need to reinitialize our plot. We also need to recalculate Sturge's rule, which we can copy from above. Now we can generate our histogram. In CairoMakie, a histogram is created by using the HIST function. Unlike the previous two histogram examples, the CairoMakie version actually gave me the 11 bins that I requested. This is what I wanted, but this may or may not be what you're looking for. So I wanted to point out that CairoMakie's histogram function is behaving differently than the stats-based histogram model. Let's add the mean and standard deviation information. Go ahead and save your plot. Now let's generate a density plot using CairoMakie. Like before, you will need to reinitialize your plot. You can generate a density plot in CairoMakie by using the density function. Add the mean and standard deviation information. Save your plot. Now this should be interesting. Here's what all of your plots should look like. Based on your needs, you can pick any one of them. When setting up all of the plots, I used a 16:9 aspect ratio, which is the aspect ratio for all modern computer monitors. The saved outputs from GR and CairoMakie are in the 16:9 aspect ratio, as expected. However, the saved outputs from the PlotlyJS plots are in a non-standard aspect ratio that I do not recognize. I tried to use several different aspect ratios, as well as different file formats, but the saved output was always the same. While it may be convenient for a plotting package to generate the linear regression line for you automatically, you still need to run the GLM model to get the formula for the line and to calculate R². Unless the plotting package is also providing you with that information, you're better off just generating this information manually, since you're going to need it anyways. When generating histograms, it's best practice to remove the gaps in between the bins. For bar plots, it's best practice to leave a gap in between the bars so that the bar plot is not mistaken for a histogram. The quote-unquote histogram that I generated in GR was done manually using a bar plot, so that's why there are gaps in between the bins. This has nothing to do with either plots or GR. The density plots definitely look nice, but with small datasets, they can be misleading. In our example, there are gaps in our data, which are clearly visible in the histograms. However, you would not be aware of that if all you saw were the density plots. So there you have it. You have several statistical plotting options available to you when using Julia. If we spent more time, we could add more settings to all of the plots to make them look better. However, these examples will give you a feel for what the plots look like straight out of the box. The plotting package you decide to use will depend on your particular situation. Each option has their strengths and weaknesses, and hopefully this tutorial has provided you with some insights into the various options. These options are, by no means, the only options available. There are several additional plotting packages available in Julia, and we'll go through a few more before the end of this tutorial series. Well, that's it. Today, we got an in-depth look at some of the foundational statistics visualizations. We learned how to manually generate linear regressions, histograms, and density plots. We also learned how to easily generate them using various plotting packages. Next week, we'll get an introduction to the data frames package. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. New tutorials are posted on Sundays. If you have any questions, please post them in the comments below. Please feel free to share these videos since these tutorials are getting rave reviews. Just listen to what the professional reviewers are saying.
Utterly repulsive.